This successful racehorse has developed a lameness in one of his hind legs. So far, routine tests such as X-ray have not been able to identify the problem. To help unravel this mystery, veterinarian Gareth Dunkley is performing a bone scan using a product known as a radioisotope. This is just one of the many ways that radioisotopes are used in our everyday lives. The elements that make up our world can exist in different forms, called isotopes. The word isotope comes from the Greek words iso, meaning same, and topos, meaning place. Different isotopes of the same element occupy the same place on the periodic table because they have the same number of protons. Their atomic masses are different because they have different numbers of neutrons. The atomic mass on the periodic table is a weighted average of all the isotopes of that element. Most isotopes found in nature are stable. The forces in the nucleus allow the protons and neutrons to coexist. In others, however, the arrangement of protons and neutrons is unstable. These are known as radioisotopes because their nuclei change or decay to a more stable state, giving off energy and matter as radiation. The main products of radioactive decay are alpha particles, or helium nuclei, beta particles, or electrons, and gamma-ray photons. Like X-rays, gamma-ray photons are high-frequency electromagnetic waves. These are all examples of ionizing radiation. That is, when they collide with an atom, they can remove one of its electrons. Due to their charge, size, and mass, alpha particles readily ionize atoms in their path. They rapidly lose their energy and don't travel very far. A layer of skin will absorb them. Beta particles are smaller, lighter, and carry less charge. They cause less ionization per unit of distance, and therefore travel further. Beta particles can penetrate living tissue, and it takes a few millimeters of aluminium to absorb them. The thickness depends on the beta particle's energy. Gamma rays have no charge or mass. They travel the furthest before colliding with an atom, and are therefore highly penetrating. Lead is used to stop gamma rays. Several centimeters may be needed for absorption, depending on the energy of the gamma ray. In medicine, the penetrating properties of gamma rays are used for looking inside our bodies. In a technique known as nuclear imaging, a radioisotope is introduced into the body. It's tagged with a compound that carries it to a specific tissue, such as the bone. A detector then measures the emitted gamma radiation and forms an image. Abnormal tissues take up more or less radioisotope than the tissue around them. They therefore give off more or less radiation, producing a dark or light area on the image. The radioisotope used most widely in nuclear imaging is technetium-99m. The M means it's a metastable isotope, which becomes more stable by giving off gamma rays. Technetium-99m becomes simply technetium-99. This is known as isomeric transition. Technetium-99m has a relatively short half-life of 6 hours. In other words, its radioactivity is reduced by half with every 6-hour period. After 60 hours, or 10 half-lives, it has less than 1/1000th of its original radioactivity. This rapid decline in radioactivity limits the exposure of the patient to radiation. Everyone on Earth is constantly exposed to radiation. Some of this is non-ionizing radiation, including visible light, UV and infrared light, radio waves and microwaves. We also experience ionizing radiation, most of which comes from natural sources. These include radioisotopes in the Earth's crust, radon gas given off by rocks and soil, and radioisotopes that occur naturally in food. Some also come from cosmic rays from the sun and outer space. A certain amount of artificial radiation comes from medical procedures. Ionizing radiation is a potential hazard because the removal of electrons from atoms can kill living cells or alter the way they function. Alpha particles are highly ionizing. However, since they can't penetrate the outer, dead layer of skin, they only pose a threat if taken into the body. Beta rays can damage internal tissues, but they can also affect the skin and eyes if these are exposed directly. Gamma rays pass right through the body, but they cause relatively little ionization, so it takes more gamma rays than alpha or beta particles to damage living tissue. The likelihood that radiation will affect our bodies depends on the dose that we experience. The dose at which effects on our health can be detected is about 250 times greater than our average annual exposure. High doses of radiation from beta particles are used in radiotherapy to kill cancer cells, but only a small part of the body is affected. The radioisotopes selected for nuclear imaging can produce just enough gamma rays for a scan, while delivering a low dose of radiation to the patient. These kinds of isotopes don't occur naturally, so they have to be manufactured. Most are made in a nuclear research reactor. Manufacture of artificial radioisotopes is one of the functions of the Australian research reactor HIFAR, operated by the Australian Nuclear Science and Technology Organisation, or ANSTO. Materials used to make radioisotopes can be placed at various locations within the reactor. There they are bombarded with neutrons produced by the fission reaction within the core. Some radioisotopes are produced by the capture of neutrons in the starting materials. Technetium-99m is produced from uranium-235. Neutrons split the uranium atom, giving molybdenum-99 and various other elements. Molybdenum-99 undergoes beta decay to give technetium-99m. Since technetium-99m has a short half-life, it has to be used quickly. Molybdenum-99, on the other hand, has a half-life of 66 hours. So nuclear scanning facilities are supplied with molybdenum-99 inside a device known as a technetium generator. Technetium-99M is then collected or milked from the generator shortly before it is needed. The thick lead walls of the generator protect the operator against gamma radiation. Here, Gareth is drawing up freshly milked technetium in preparation for his equine patient's bone scan. Although the dose to the patient is low, staff who are regularly involved in this procedure take precautions to reduce their long-term exposure to gamma radiation. They wear lead gowns and carry the technetium in lead-lined containers. Before the technetium is injected, the horse is given a sedative. This drug also increases blood flow to the bone.
And next comes the technetium.
The technetium has been tagged with a compound that will bind with the horse's bones. Materials used for the injection are discarded after 60 hours when 10 half-lives have expired. The horse stays in its box for 2 hours to allow the technetium to be taken up by the bone. As the technetium decays, it gives off low levels of radiation. The intensity of the radiation decreases with the square of distance. Doubling the distance from the horse reduces exposure by a factor of 4. So staff are able to limit their exposure by keeping their distance from the horse. When the horse is ready for scanning, a gamma camera is used to detect gamma rays from different angles. This gives a series of planar or two-dimensional images that are transferred onto film. So, what's the verdict for this patient?
On this bottom part of the cannon bone here, this distal part of the cannon bone, which is in the fetlock joint, you can see that there's quite a dark area in some of these shots. And this just indicates that there's an increased uptake of the technetium in this part of the bone. So there's increased binding sites here, and there's increased amounts of gamma rays being emitted from this region.
This indicates a stress reaction, a change in the function of the bone. This is hard to find using X-ray, which mainly detects structural changes, such as fractures. In human medicine, nuclear imaging is a vital tool for diagnosing various forms of illness. In a procedure known as single photon emission computed tomography, or SPECT, the camera moves around the patient, detecting gamma rays from many different angles. The word tomography refers to the mathematical process that's used to convert gamma emissions recorded by the camera into a series of images. Each image represents a slice through a different layer of tissue, in this case, of the heart. This technique provides valuable information about both the structure and function of different organs. This is the inside of a camera used in a form of imaging known as positron emission tomography, or PET. In PET scanning, patients are injected with a radioisotope that decays by emitting a positively charged beta particle, or positron. Positrons are emitted by radioisotopes that are deficient in neutrons. Fluorine-18, for example, becomes stable by converting a proton into a neutron. To balance the charge, a positron is emitted. Inside the body, positrons given off by fluorine-18 travel only a few millimeters before colliding with an electron. The positively and negatively charged particles annihilate or cancel each other out. However, their energy and momentum are conserved by the formation of two gamma rays that are emitted in opposite directions. These gamma ray pairs are detected as the patient is moved through the camera. Fluorine-18 can be chemically bound with glucose. This makes PET scanning particularly useful for looking at tissues that use a lot of glucose in their metabolism. These include the brain, heart, and some malignant tumors. This scan shows a tumor in the lung and skin. The kidneys and bladder also show up because fluorine-18 is excreted in urine. Neutron-deficient radioisotopes such as fluorine-18 are made in a cyclotron. About 1/5 of the medical radioisotopes needed in Australia are produced in this cyclotron operated by ANSTO. The radiation produced by a cyclotron decreases quickly when the machine is switched off. So during a routine shutdown for maintenance, it's safe to enter the cyclotron vault. The vault has thick concrete walls that block the radiation produced when the cyclotron is operating. Inside the cyclotron, hydrogen gas is passed through a series of electric and magnetic fields to produce protons that travel through a vacuum at 1/4 the speed of light. These protons are directed down a beam line at a target in a separate room. For making fluorine-18, the target is oxygen-18.
The process is you have O18, where 18 is the atomic mass. We actually bombard it with protons, so one proton goes into the nucleus, it knocks off a neutron, and so the atomic mass is the same. But the atomic number has changed because you've added the proton, and so that's why it goes from oxygen to fluorine.
The fluorine-18 then goes to a sterile laboratory where it's combined with glucose. The material is handled remotely to protect operators from positron and gamma radiation. Just as we need to look inside the human body, so too we need to examine man-made structures to make sure that they're in working order. Radioisotopes allow us to do this without damaging materials or dismantling complex equipment. For example, gamma radiography is used to check the components of the turbine inside a jet engine. Instead of a camera, this procedure uses film that is blackened by exposure to radiation. The operator inserts a guide into the engine until it's level with the film. The guide is connected to a housing containing a radioisotope. In this case, it's iridium-192. This is made in a research reactor. Its half-life is 74 days, so it can be used for up to several weeks before its activity gets too low. The radioisotope is pushed into the engine using a remote winding mechanism so that the operator can stay away from the radioactive source. When the isotope is in place, gamma rays pass through the engine onto the film, forming an image of the parts in between. While the image is created, the operator monitors a radiation meter to check that the radiation is within safe levels. Like all people who work with radioisotopes, he also wears a monitor that records his exposure over time. When the film is developed, the engine parts show up white, where the metal has blocked the gamma rays. Damaged components, like the one on the left, can be easily distinguished from normal ones, and can then be replaced. The most frequent use of gamma radiography is checking for defects in metal castings or welded joints, such as those in pipelines. Defects show up in various ways. This dark line shows a failure of the metal surfaces to join. Radiation is also used to measure or gauge the properties of materials. This road is being made to strict specifications to ensure that it will stand up to the pressure of heavy traffic. After each layer of the road is laid, its density is checked using a densitometer or density gauge. A series of holes is spiked in several random locations. Then, the densitometer's probe is inserted into each hole. The tip of the probe contains cesium-137, which gives off gamma rays. These are scattered as they bump into atoms in the road, giving gamma rays of different energies. Medium energy gamma rays pass into a chamber where they are counted over a 1-minute period. The more dense the road, the smaller the number of counts per minute. Radioactive gauging has many applications. In this factory, it's used to measure the amount of wood fibre in pulp that is used to make fiberboard. When a plant is exposed to carbon dioxide containing radioactive carbon-14, the parts of the leaf that use carbon for photosynthesis will show up black when the leaf is placed onto film. This is because the carbon-14 emits beta particles that expose the underlying film. The resulting autoradiograph takes hours or even days to produce, as the half-life of carbon-14 is greater than 5,000 years. Shorter-lived radioisotopes are used to trace industrial waste and sewage, and to monitor the movement of sand. Information from these studies helps us to better understand and protect our environment. The forms of radiation produced by radioisotopes are tools that we can call on in order to look inside our bodies and to monitor the world around us. Thanks to his encounter with radioisotopes, our racehorse is off to the paddock to enjoy a well-earned rest.